4 species, none of them true crabs, trace their ancestry back farther than the dinosaurs, yet their blood keeps modern medicine alive. Scientists call them Dizyphosaurids, survivors unchanged in silhouette for hundreds of millions of years. But every rule about evolution, survival, even family ties, is twisted in their story. Why does everything about the so-called horseshoe crab defy logic? And what deeper secrets are embedded in its ancient bloodline? Horseshoe crabs are imposters in their own name. With a hard shell and a spiny tail, they scuttle across mudflats like crabs. But they are not true crabs, and they are not crustaceans. Instead, they belong to the order Xiphosaurida, a branch of arthropods known as chelicerates, the same group that includes spiders and scorpions. The 4 living species, Limulus polyphemus along the Atlantic and Gulf coasts of North America, Tachypleus tridentatus and Tachypleus gigas in East and Southeast Asia, and Carcinoscorpius rotundicauda in Indo-Pacific mangroves, share a lineage that split from crustaceans long before the first true crabs scuttled across the sea floor. Unlike crustaceans, horseshoe crabs have no antennae or mandibles. Their first pair of appendages are chelicerae, specialized feeding claws found in arachnids. Some genetic studies place them just outside the arachnid family tree. Others nest them within. But all agree, the so-called horseshoe crab is closer to a spider than to any crab. What force could keep such an odd lineage alive while the world changed around it? Imagine an animal older than most life on Earth, its relatives preserved in rocks that are 445 million years old, long before the first dinosaurs or flowering plants. Through the end Ordovician extinction, the chaos of the Permian, and the asteroid that ended the age of reptiles, its armored outline persisted. The fossil record suggests a living fossil, but that label hides a mystery. But beneath that ancient shell, the story is not one of simple stasis. While the basic body plan, a broad carapace, a spiny tail, and walking legs, remained effective in shallow, shifting seas, their genomes tell a different tale. Horseshoe crabs have experienced unusual bursts of gene duplication, including multiple copies of Hox's genes that shape animal development. One leading theory suggests this genetic flexibility may have allowed subtle adaptation, even as their form stayed remarkably stable. Genomes can change in ways that do not always show up in the skeleton. The world around them transformed. Oceans rose and fell, continents drifted, new predators appeared. Yet the horseshoe crab design kept working. The question is not why they failed to change, but why this particular blueprint kept surviving while so many others vanished. What features made this body plan so enduring? A horseshoe crab is built for survival in shallow, shifting seas. Its prosoma forms a single helmet-like shield, fusing head and thorax beneath thick armor that deters most predators. This protection comes with a price. The crab moves slowly, its body stiff and awkward on land. Along the shell's edge, spines guard the softer abdomen, where 5 pairs of book gills unfold, each with about 150 thin lamellae, maximizing oxygen exchange, but easily clogged by silt or pollution. The long, rigid telson is not a weapon, but a lever, flipping the crab upright when waves turn it over. 10 eyes scattered across the shell and tail sense light, shadow, and the pull of the tides. On the underside, legs tipped with spiny natto bases grind food straight into the mouth. Growth is slow. Juveniles molt up to 17 times, risking exposure for a decade before reaching maturity. Every feature is a calculated compromise. Inside every horseshoe crab flows a blue blood unlike any other, colored by copper, not iron, and charged with a chemical defense that has quietly reshaped modern medicine. The secret is in their amebocytes, immune cells that swarm and clot instantly around invading bacteria. In the 1960s, Dr. Frederick Bang and Dr. Jack Levin discovered that just a trace of bacterial endotoxin could trigger this reaction, causing the blood to gel solid in minutes. That insight led to the creation of Limulus amebocyte lysate, spelled LAL, a life-saving test so sensitive that it became the global standard for detecting endotoxin contamination in vaccines, intravenous drugs, and surgical implants. Today, hundreds of thousands of horseshoe crabs are captured each year along the Atlantic coast, bled of up to 1/3 of their blood, and then released. Studies show that many survive, but others do not. Mortality rates after bleeding can reach 10 to 30%, with additional hidden costs in impaired movement and missed spawning. The world's dependence on this ancient immune chemistry has created a new kind of pressure, one that ripples far beyond the laboratory. How do we reconcile a test that protects human lives with the toll it takes on the animals that make it possible? The answer is neither simple nor settled. On the beaches of Delaware Bay, a single night's tide can unleash a spectacle that ripples across continents. Tens of thousands of horseshoe crabs converge to lay eggs in the sand, each female burying clusters of pale green spheres just beneath the surface. For the red knot, a sandpiper flying from the tip of South America, this moment is everything. The birds arrive exhausted, their reserves nearly spent, and in just 2 weeks they gorge on the eggs until some nearly double their body mass. This nutrient pulse fuels the last leg of a journey to the Arctic, where missing the window means missing a year's chance to breed. Volunteers walk the shorelines, counting birds and crabs, tracking a chain of survival that links ancient tides to a bird's fragile future. What happens if this chain breaks? In 1998, the Atlantic States Marine Fisheries Commission set the first coast-wide cap on horseshoe crab harvest, freezing removals at already elevated levels. Yet new threats keep multiplying. Artificial lights along developed beaches now disrupt the moonlit queues that guide crabs to spawn, shrinking safe habitat with every new bulb. Meanwhile, synthetic alternatives like recombinant factor C promise relief for biomedical demand, but adoption remains scattered, and regulations and industry habits lag behind the science. The future for horseshoe crabs is tangled in policy, technology, and shifting coastlines, with no clear resolution in sight. Right now, human demand for horseshoe crab blood outpaces their recovery. Modern medicine depends on an ancient survivor, yet its fate hangs on choices we make this decade. What survives and why is up to us.